Now we're going to talk about the always fascinating question of what makes a big giant steel boat float? And that's an idea that we have to understand buoyancy to get to the bottom of. So why do some objects sink and some objects float? To think about that, we need to think about pressure. And this is going to lead us to what's called Archimedes Principle. But let's think about this box, a red box floating in a pink fluid. As we go down in the fluid, we know the pressure is going to increase, right, from our fluid static. So the deeper I am, rho GH, bigger my H is here, the bigger the pressure is. So my pressure here is modest, it's a little bigger here, and it's a lot bigger there. Well, in a horizontal direction, what are the pressures, overall pressures on my red box? They're going to balance out. This one is going to balance this one. This arrow is going to balance that one. And so we don't get any movement in the horizontal direction, no force in the horizontal direction. In the vertical direction, though, we have bigger arrows down here than the small arrows up here. So the force on the bottom of this box is larger than the force pushing down on it, and that's our buoyancy force. The difference between these two forces is our buoyancy force, the thing that's pushing this object up. Now, why doesn't everything float then, right, if you have a force at the bottom? Well, think about a free body diagram of my red box. I have a buoyancy force that's going up, right, because these forces are bigger than those forces. What other force is affecting my red box here? Well, it's the weight force, right? So if my weight force is bigger than my buoyancy force, I'm going to sink. If my weight force is smaller than my buoyancy force, then I'm going to rise, then my object is going to rise up. And Archimedes' principle is just a statement of what we've just seen. When a body is completely or partially submerged, the upward vertical force exerted is due to the pressure difference between the top surface and the bottom surface. And here's another picture of that if we want a 3D version of that. And here we start to quantify, hey, look, we know what the pressure is here. We can find the force by multiplying it by the area. And then we can find the force down here, and we can start to figure out, well, what is your buoyancy force? So let's do that. The math is a bit complex, but it turns out in any shaped object, not just a rectangular or a nice cylinder, it turns out that the force, the buoyancy force, is equal to the weight of the fluid that is displaced. So if I have a styrofoam box in water, the buoyancy force has to do with the volume of that styrofoam box, but the density of the fluid itself, not the styrofoam. Okay, so my buoyancy force is the weight of the displaced fluid, which we know is mg. So the mass of the displaced fluid times gravitational constant. Well, what's the mass of the fluid? It's the volume of the displaced fluid, or displacing object, my styrofoam box, times the density of the fluid. So all of these, this one, that term, and that term, are all the same thing. This one ends up being useful to us because when we talk about fluid, we want to talk about density and not just mass. Now, whether an object floats or not is determined by whether this guy is bigger or smaller than the weight force on the object. Well, what's your weight force? It's the mass of the object times g. And we could translate that into a density term here. It's the density of the object times the volume of the object times g. Okay, and you can see then this volume of the object is here and it's also here. And so the thing that determines which of these is bigger is my object more dense or less dense than the fluid itself? So let's look at this image over here because I think this is a nice way of thinking about this. If I have a styrofoam box I'm displacing a lot of water, right? My V displaced is big. My rho fluid is still big because water still has a large density. So my buoyancy force is large, but my weight force is really small, okay? Because the rho of my object, the density of styrofoam, is really small. And so the buoyancy force rises that box. If my box is made of lead instead, I have the same buoyancy force because it's displacing water. There's nothing in here about styrofoam or lead, right? But my weight force is much bigger, and so this is going to sink. If the two are equal, it's going to float, okay? It's going to float no matter where, whether it's on the surface or whether, if I just leave it in the center of the fluid, it's going to stay in the fluid. It's what we think of as being weightless, okay? But it's really not weightless. It's just the buoyancy force is balancing the weight force. And then finally, if I have that box of styrofoam, as it goes above the water, what happens to its mass? What happens to its weight force? Nothing, right? The weight force stays the same even if it goes out of the water. But what happens to its buoyancy force? The volume of displaced fluid becomes smaller and smaller as I rise out of the water. And so even with my styrofoam box, my weight force is going to stay the same, but my buoyancy force is going to go down until they're balanced. And when they're balanced, it's going to float with some portion of that object outside of the water. This is tricky, and we'll work on this in class, trying to get this idea. But let's do a little bit of a practice here. So let's say I have a 1,200 kilogram cube of plastic that's 1 meter cubed on all sides. Why do I have this giant cube of plastic that's really, really quite heavy? Does it float? Well, we want to find out if the net force is positive or negative, right? We have two forces acting on our object. We have a buoyancy force pushing up and a weight force pulling down. My buoyancy force is the rho of water times the displaced volume times G. Okay, here's my rho of water. Here's my volume displaced, and there's my G. So the buoyancy force amounts to about 10,000 newtons. The weight force, on the other hand, is just the mass of the cube, which we're given in the problem, times G, which is almost 12,000 newtons. So the weight force is pulling down more than the buoyancy force is pushing up. We find the sum, and we can find the weight force, or the net force on our cube is downward. So it's going to sink. And here we could think about how fast it's going to accelerate, right? We know what the force on that object is. We know its mass and all of that stuff. And so we know that that object is going to sink. We could have looked at this initially and said, wait, this has a density of 1,200 kilograms per meter square, or meter cubed, right? That's more dense than water. And if it's more dense than water, it's going to sink.